We're now going to do a bit of an experiment, and that experiment is going to involve the Pitot static tube. So in the last segment we talked about the Pitot static tube as being a device that you can use to measure velocity in a flow. And what the Pitot static tube involves is basically a tube within a tube. And so we have an inner tube, and then we have an outer tube wrapped around that. And in this outer tube, there would be another tap. So that measures P static, and this one here measures P total, or P naught. And in the side of the tube itself, there's going to be holes, and that enables us to measure the P static. And then up here, the flow is going to stagnate, and so that's where we're measuring P naught, where velocity goes to 0 along a streamline. And we saw in the last segment that we said that we have a way to be able to calculate the velocity based on the pressure measurement, or the difference in pressure between P naught minus P infinity divided by the density of whatever fluid we're looking at. So that would be rho of whatever fluid. If it's air, that would be the density of air. So what we're now going to do, we're going to take a look at a video clip with a Pitot static tube, and then we're going to make a velocity measurement by measuring the pressure differential using an inclined manometer. So let's take a look at that video clip now. So what we have, that's an image of a Pitot static tube. I'm zooming in on the front of it, and you can see the static port. That's looking from the front where you see the total pressure port. And then as we angle it, you'll be able to see both the total at the front and the static pressure tap on the side. Here's another Pitot static tube, and there you can see the taps at the end of it. And then when we look at the front of that Pitot static tube again, you'll see a total pressure tap and then the static pressure tap on the side. And that's where we measure the total pressure and the static. And here's an inclined manometer. We're going to hook the Pitot static tube up to the inclined manometer. One tube goes to the static, one goes to the total. Let's see what happens when we turn on a flow and put the Pitot tube into it. We can see that the manometer is increasing. I've sped this up because it takes a while with this fluid to react. We're going to measure that. We get 0.0475 inches of water. And with this inclined manometer, it's been calibrated at sea level, so that's 850 feet per minute. So what we're now going to do, we're going to do some analysis of that. So if you recall from the video, it said 0.0475 inches of H2O measured by the inclined manometer, and it also had a calculation 850 feet per minute, but I have to say that that is at sea level. And the experiment that you just watched was performed in Calgary, and the pressure was around 89 kPa. So the 850 feet per minute will not be accurate, and we'll see that as we go through the calculation. So to begin with, the inclined manometer is giving us a pressure measurement, and that was in inches of water. So I'm going to convert that. Inches of water, I don't like working with British units, so I'm going to convert that to SI. So we get our delta H. We can then take that and equate that to the difference between the total pressure tap and the static pressure tap. And in order to do that, we have to convert inches of water into a pressure. So that's rho of water, G, delta H, plugging in the values. we get 11.84 pascals. So that's a low pressure, but that's what we're getting. Now, in the Bernoulli equation, let's take a look at it again. Remember, we have this density here. That is rho air at local conditions. And as I mentioned, this experiment was done in Calgary, probably around standard atmosphere in terms of temperature, so 15 degrees C. So what we're going to do, let's calculate the density of air. And that will be P over RT, where P 89,000 plus or minus a couple hundred pascals, but not a big deal here. 287 for the universal gas constant, and then assuming about 15 degrees C, 288 K. With that, we get 1.0768 kilograms per meter cubed. So I'm going to take this, I'm going to take my delta P measurement, and we're going to take it and we're going to put it into this equation here for the pitot tube, enabling us to then determine the velocity. So when we do this, we get about 4.69 meters per second is what the pitot tube was exposed to. Now I'm going to convert that to British units because that's what we had on the inclined manometer, and I just want to take a look as a bit of a sanity check to see how close we are. So we have feet per second, but that was in feet per minute, so I have to convert that to feet per minute. And what we get is 923 feet per minute. And the inclined manometer had been calibrated, and it was giving us a value of 850 feet per minute. So there's an error there, and the source of that error comes from the fact that when I calculated density here, I used a pressure of 89 kPa versus 101.325 kPa. So let's take a look at what happens if we make that correction and do this calculation at sea level, which it really wasn't, so that would be incorrect. But if we had said if density of air was evaluated at sea level, and at sea level the pressure would be 101.325 kPa, we would then come up with a velocity measurement using Bernoulli's equation and this pitot tube equation of 865 feet per minute, which you can see is quite a bit closer to the one that I read off of the manometer from the video. But that would be if you were to do this experiment at sea level. For where I did do the experiment, the correct velocities are the ones that we have here. So 923 feet per minute, or 4.69 meters per second. So that gives you an example of making a measurement using the pitot tube. I showed you it using an inclined manometer, but you can use an electronic pressure transducer or any other type of pressure measurement in order to figure out what the delta P is on the pitot tube. That gives you an application of pitot tube for velocity measurements.